there, welcome to the video about the domain, the range, the intercepts, and the end behavior of functions. So these are all things that can happen or not happen to, but functions have. And yes, this is a function, isn't it? So let's talk about domain. The domain is just another name for the inputs of our different functions. We've been evaluating functions. The range then is the outputs. So another name we use for domain and for inputs, those are our x values. And so the range and our outputs are our y values. Sometimes we use the phrase independent variable, and therefore then the output, the y values, the range is our dependent variable. So when you're asked to find the domain and the range of a function, you list the domain as these things, whatever your inputs or your x values are, or if it's just sort of a concept what the independent variable is. And then therefore your range depends on what your domain is. That's why it's the dependent variable, and you just list those outputs or y values. So if I wanted to find the domain and range of this function here, by the way, how do I know that this is a function? There's no repeating x values. So I could say my domain is just all my x values. In this case, it's just going to be 3 and 5 and 9 and 22. And my range is going to be my y values, 5 and 8 and 13 and 18. It's as simple as that. If we have specifically a linear function, I know it's a function because it passes my vertical line test. In fact, I can even write an equation for this. This is the function f of x equals, let's see, looks like we're starting at 2. It's going to be 3x plus 2. This f of x part is so I can plug in values to get this, but I can also write this just as y equals 3x plus 2. Those are equivalent forms. The domain is going to be all of the x values that I'm using in my function. And since this line is going to extend forever in both directions, I'm using all of the x values this way and all of the x values this way. I'm not limited in my use of x values at all. I could plug in 1, I could plug in 1.5, I could plug in 500, I could plug in negative 10.2. So my domain is all real numbers. And since you remember our types of numbers discussion from the beginning of the year, real numbers are any numbers you can place on a number line. It includes all of our rational and irrational numbers. Well, if I'm using any x values this way and any x values toward the negatives as all of my inputs, then all of my outputs, my y values, can be anything this direction and this direction. So I have all real numbers as possible outputs as well. All real numbers, possible outputs. So linear functions are very wide open in that sense. Typically, for any linear function, the domain is all real numbers and the range is all real numbers. The intercept we're looking at is typically we're looking for the y-intercept, and in this case, where the y crosses the y-axis, and so it's right there at the y-intercept equals 2. Sometimes functions ask for the x-intercept, where it crosses the x-axis, and in this case it looks like it's about right there. I'm going to estimate that to be negative 2/3. Okay, so it's where the function crosses the axes, either the y-intercept or the x-intercept. When we talk about end behavior, we talk about what happens at the ends of the functions. I had already drawn these green arrows on here. As x keeps increasing, what happens to y? It keeps increasing. So we say, as x approaches, with the arrow, infinity, sideways 8 means infinity, then y also goes towards infinity. And as x approaches negative infinity in the negative direction, x is going this way, y is getting less and less and less, y also approaches negative infinity. So that's just some notation talking about what's happening at the ends of the function. If we look at an exponential function, it looks a little bit different. This looks to be the exponential function f of x equals, I think it was crossing at 1, so 1 times 2 to the x power, or we can say y equals 1 times 2 to the x power, so we can use f of x or y equals. And hopefully you're noticing this also just continues on and on and on, getting closer and closer and closer to 0, but it's never going to actually touch 0, is it? And this keeps going up and up and up and up and up. And notice I just have my window from negative 10 to 10, just a standard scale, which is typically what we look at for the exponential functions. So in this case as well, because it keeps going off in both directions, my domain is still all real numbers. But hopefully you're seeing that my range, my y values, are just limited to the top half of my graph. I'm using all of the y values in this direction, but I'm never going below when y is 0. So I'm not using down here at all. Not using. So what we say is we're just using the y values that are greater than 0, because this is never going to touch 0. Okay, it just gets closer and closer, and it certainly looks like it's 0, but it never technically touches it. The y-intercept here, pretty easy to see, it crosses at 1, so it's crossing the y-axis at 1. And since we just said it never touches 0, there's no x-intercept. And then the end behavior is also going to be a little different, because we said, let's see, as x goes to infinity, y also goes to infinity, because it's going to get bigger and bigger and bigger, a lot faster than linear functions, but it's getting bigger and bigger. And as x goes negative, y isn't going to go to the negative. We just say y approaches 0. It's never going to actually get to 0, but it gets closer and closer and closer and closer and closer to 0. Just to compare that, because I want to show you the exponential function in a bigger window, if you notice, I changed the window settings here from 50, negative 50 to positive 50 for the x-axis, and I didn't use the bottom half at all because I know we're not going to go down there. And then this is by 10 thousandths. So just to get a sense of how quickly exponential functions grow, by 10 on the x, we're at 1, 2, 3, 4, 5, 6, 7, 8. We're close to 10,000 on the y values. So as this is just to emphasize, as x gets bigger towards infinity, y gets also towards infinity, but you almost want to put stars around this because it gets really big really fast. Really big. Oops, my pen's not running. Big, really fast. Let's see. If we put some equations in a calculator, here we just have the linear one that we had before, y equals 3x plus 2. And just to make this one more similar, if we do y equals 3 times 2 to the x power, so we're using the same numbers, but if we look at the difference between a linear function in blue and the exponential function in red, notice that the y-intercept for the linear function is the 2 that's right here, and the y-intercept for the exponential function is the 3 that we're starting with right here. Okay, and the linear function goes off in both directions very happily forever and ever. Whereas the exponential function starts to get really big really fast. You can see how big these numbers are getting down here, and this just gets closer and closer and closer to 0, never technically touching 0. Let's look at the last page. Here's a little example that you might see on a standardized test, and it says, sorry it's so small, but it says the figure below shows the graphs of the exponential functions f of x equals c, so some variable, times 3 to the x, and g of x equals d times 2 to the x, for some numbers where c has to be greater than 0 and d has to be greater than 0. So that just means we're not going to have negatives. They intersect at the point PQ. And we're going to only try and answer this part here, part A. So some number that's 3 to the x and some number that's 2 to the x, how do we know which is which? What I would say, and hopefully you're saying to yourself, is that if I'm going times 3 each time, this is times 3, and this one is times 2 each time, then the times 3 is going to get bigger faster. So this one is going to be c times 3 to the x power. And this one, multiplying, so it's still exponential, but it's not as fast because I'm only multiplying by 2 each time. This is the difference between doubling and tripling. Then this is going to be the lower curve. Now, when you go backwards and sort of look to where they cross down here, that means that this d is our y-intercept and this c is our y-intercept. So which is greater, c or d? We can say that d is greater than c because as y-intercepts, the d is higher than the c. And then this, I know d matches up with d times 2 because it's just doubling, and this c matches up with c times 3 to the x because that one is tripling. So this is just an example of how you might have to apply your knowledge of intercepts and how exponential functions work. I think that's it for today. Just remember with domain and range, D comes before R in the alphabet, just like your X comes before Y in the alphabet, X, Y, Z. So we know domain is always what are the X values that we're using, and range is always what are the Y values that we're using. Hope this helps. Please let us know if you have questions.